In this video, we're going to take a look at how to use the technique we've been learning about solving differential equations that are in a particular form, the exact form, how to use that technique on some differential equations that may not be exact but can be put into a form so that they're exact. It's a little bit involved, and it doesn't happen very often, and in fact, we're going to have to make some pretty big assumptions in order to be able to do some of these problems. But I'll explain that along the way as we go through this video. Let's take a look at the equation 3x squared y plus 2xy plus y cubed plus x squared plus y squared quantity times y prime equals 0. At first glance, this looks like it might be an exact differential equation. If this is our m and this is our n, but we have a way of testing that. So let's go ahead and do that first. We're going to check and see whether m's partial derivative with respect to y is equal to n's partial derivative with respect to x. M's partial derivative with respect to y assumes that x's are constants. So the derivative of a constant times a linear factor is just the constant. That's going to give me 3x squared. Plus, same thing here, the derivative of a constant times a linear factor is just the constant. I'm taking this with respect to y, so I have then plus 2x. And then I have the derivative of y cubed with respect to y is 3y squared. And then for n, I'm going to take the derivative with respect to x. The derivative with respect to x of x squared is 2x. And with respect to x, the derivative of y squared is 0. So I have my partial derivative of m, this expression here, with respect to y, and my partial derivative of n with respect to x, and they are not the same. These two things are not equal. So this is not in exact form. It's not an exact differential equation. Once upon a time, I think it was back in, I think it might have been all the way back in section 2.1. Let me see if I can find that real quick. Yeah, it was. In 2.1, we did something called finding an integrating factor that we could push through the equation, and that would turn it into a form that would allow us to use a previously learned technique. We're going to do something similar here. I'm going to find an equation u of xy, a function rather, u of xy, so that u times 3x squared y plus 2xy plus y cubed plus u times x squared plus y squared times y prime is equal to u times 0. Of course, that's 0. And when I do that, this will become my new m. I'll call it m1. This is going to be called n1. Right? These are my 0th m and n. These are my first m and n. Now, it's much more complicated than that, but I wanted to put that out there on the screen to help you see what it is we're going to try to accomplish in this video. This is the goal. First of all, to determine whether or not a function is, a differential equation is exact, and we know how to do that now. We do this little trick over here. Having done that and it's determined that it's not an exact differential equation, our next goal is to try to figure out whether, because it's in the form that it's in, right, m plus n times y prime equals 0, if it can be made into an exact differential equation. And if it can, it will be by finding a function u and multiplying every term by that function u, turning it into, hopefully, a differential equation that is exact. So that's the goal here. Unfortunately, finding that function is quite tricky for several reasons. I'll elaborate on what those reasons are as we go through here. But let's just start by backing up for a minute. Now that you know what it is we're trying to accomplish, let's back up and talk a little bit about the theory behind what's actually going on and then I'll explain kind of through this process. I'll show you a way to find that function without having to go through kind of all the long steps every time. There's kind of a shortcut, but it's important that you understand, first of all, what it is we're trying to accomplish, and second of all, how we get to that shortcut, what's really going on. So I'm going to start by writing an exact, or sorry, not an exact, may or may not be exact, a differential equation in the form that it needs to be if we're going to use the technique of exact differential equations to solve it. But let's assume for the moment that this one turns out not to be an exact differential equation, because if it is, we know how to solve them. If it's not an exact differential equation, then I want to find a function u of x and y so that my new differential equation, u times m plus u times n equals u times 0. Oh, guess what I forgot? I do that so often, but I do it often enough that I kind of got used to, I do sort of, I think I just mentally know to glance back over, and if it's missing, I notice it right away. That y prime is really critical there. So now I have, I hope, a new m, should I succeed in finding this function, a new n, or a new function in the position of n, but I still have, my equation is still in the right form, right? This would be my m plus my n times y prime equals 0. Okay, so now let's assume that having found the right integrating factor, this function u of x and y, u is a function of x and y, let's say that we've managed to find it, and in order to determine whether it is now an exact differential equation, I need to do the same thing as I would have done before. I need to take the derivative with respect to y of u times m of xy and check to see whether it is equal to the derivative with respect to x of u times n of x and y. But these are products. We need to use the product rule. My left-hand side here is going to be the first times the derivative of the second, but the derivative of the second is the derivative of m with respect to y. So I'm going to call that m sub y. My pen just did some weird things there. M sub y. Plus, because of the product rule, the second, just a good old m, times the derivative with respect, sorry, the derivative of the first. Well, the derivative of the first is the derivative of u, but again, here I'm differentiating with respect to y. On the right-hand side, we have another product of u and n. So I'm going to say that the derivative of that is the first times the derivative of the second, but this time I'm differentiating with respect to x. So I'm going to have the first times the derivative of the second plus the second times the derivative of the first with respect to x. Now in the line above, I have a question mark above my equal sign because I don't know if these two sides are equal, but in taking the next step here, I'm going to leave that off because what I'm trying to show, or what I'm trying to establish, is what u has to be in order for these to be equal. So I'm going to let them be equal. I'm going to set them equal to each other. I'm going to try to figure out what u is, right? Effectively, I'm going to solve for u, or I'm going to try to. So I'm going to rewrite this line now up here. But I'm going to do a little bit of algebra as I go along. I've noticed here that this is just a u and this is just a u. This is a u, partial of u with respect to y, and this is a partial of u with respect to x. So what I'm going to do is isolate on one side the terms that have just a u in them, and on the other side the terms that have a partial derivative of u in them. And I think I'm going to put my u's on the right-hand side. So I'll put my equal sign there. I'm going to say u times n sub x, and that's already on the right-hand side. I'm also going to subtract this quantity from both sides. That's going to give me minus u times m sub y. On the left-hand side, I have m times u sub y minus subtracting that other term, subtracting this term from both sides. Nope, so this term from both sides, n times u sub x. So minus n times u sub x. And then I can factor out the u on this side here. So I get, I'll rewrite this as u sub y m minus u sub x n equals, factor out the u, and I get n sub x minus m sub y. Now, this equation is, if we're looking for u here, and really what this is if I could integrate both sides here, right, I'd need to be able to integrate partially. I'd need to be able to unpartially differentiate. So what that makes this equation, this differential equation, is a partial differential equation. And we are not going to be building the skills in this course at all that would help us solve a partial differential equation. If you go on to take higher mathematics, you may run into a course called partial differential equations. It is an entire course. There are multiple courses, but this is not a course in partial differential equations. It's a course in ordinary differential equations. So we can't solve this. However, under certain conditions, under certain restrictions, we can still use the techniques that we've learned about how to solve exact differential equations to solve one that you might call almost exact. This equation up here is almost exact because I will eventually find a function u that I can push through that makes it exact. It puts it into an exact form. The question is, how do you find that u if you can't solve this equation? I don't even know what m and n are in this original equation, and I'm already telling you we can't solve it. Well, we can't solve it as it is, but what we can do is we can make an assumption. We can say, with the tools that we have at our disposal, we can say, imagine with me for the moment that u is not a function of x and y, but just a function of x. In other words, there are no y's in it, right? Let's make that assumption just for the moment. Then when I look back at this line right here, I get this additional information. If u is only a function of x, then when I take its derivative with respect to x, I get a new function. U sub x will be a function. But if u is a function of x, and I try to take its partial derivative with respect to y, I'll get 0, right? When you differentiate a function with respect to y, all the x's are constants. And this one only has x's in it. It doesn't have any y's in it at all. And we've restricted it. This is a function that we're looking for as a function of x and y, but we can't do that. So we're going to make an assumption. We're going to make a restriction on it. We're going to say that the function would have to be one that only had x's in it. Okay. Now, when I take the partial derivative of u with respect to x, I get whatever I get. But when I take the partial derivative of u with respect to y, all the x's in that function, their derivative is 0. Right? We're going to hold them constant. So that would make my equation here, this statement that I'm trying to use to find a way to describe u, right? I've set these two sides equal to each other, these two derivatives equal to each other. I'm solving. I've now placed a restriction on u. And what that lets me do is rewrite this equation as negative u sub x times n equals u times n sub x minus m sub y. And if I divide both sides of this equation by negative n, I get the partial derivative of u with respect to x is equal to negative n sub x minus m sub y all over n times my function u. Now, once I know what u sub x is, I'm looking for u, right? Once I know what u sub x is, hopefully all I need to do is integrate both sides. with respect to u, and I'll have my function u. Now, once I know u, I can go plug it back in here, turn this into an exact equation, and solve it. So that's the goal. The question is, how do you actually figure out what goes here? And the answer is basically you take the derivative of n, which is this guy, this guy up here, with respect to x. You take the derivative of m with respect to y. You subtract them, and you divide by this function not differentiated. Well, some of that work we've already done, right? This n sub x here and m sub y here, we already did those. And in fact, it's really interesting to note that if you subtract these here and get 0, then this one minus this one, which is this one minus this one, if that's 0, then these were equal and you didn't have to go through any of this, right? So we're going to subtract them here, not get 0, and divide by n. Now, that's the assumption that u is a function of x only. What if u is a function of y only? Because that would give us another option. And in fact, as we work through these problems, I'm not really sure which of those two assumptions I want to make until maybe a little bit farther down the road. So let's take a quick look at what happens if u is only a function of y. Before I do that, I'm going to copy, let's see, I'm going to erase a few things actually. Before I did this, we had something like this on this side of the screen. I'm going to copy this formula down. It's a formula. It's a formula, but where did we get it? We got it from, well, we got it from here, right? We got it from solving this and then making the assumption that u is only a function of x. So I'm going to write this here. If u is only a function of x, then u sub x is n sub x minus m sub y over, I'm going to write this as negative n and then times u. And what we're going to go do now is figure out what happens if u is only a function of y, then u sub y is, we don't know yet, we're going to go figure that out. So what I'm going to do now is erase back up to here and change that to a y, and then we'll work forward again. Okay, so if u is a function of y, then this equation becomes the derivative of u with respect to y times m minus the derivative of u with respect to x. But if it doesn't have any x's in it, and every term that has a y in it, the y's all get treated like constants. When you differentiate a constant with respect to x, you get 0. So this whole term becomes 0. And in fact, I don't even need my minus sign, right? Because I have minus 0 there. In that case, this is going to be equal to u times n sub x minus m sub y. Solving that for u sub m means dividing both sides by m, and I get u sub y, the derivative, partial derivative of u with respect to y, is equal to n sub x minus m sub y all over m times my function u. And once I know what u's partial derivative with respect to y is, theoretically I can just integrate both sides and I get my function u. I'm going to erase that because I don't want to leave that on the screen. What I will do is copy that little formula up here. U sub y is equal to n sub x minus m sub y all over m times u. And these two formulas are very similar. This one has a negative in the denominator and this one doesn't. This one has an n in the denominator, this one has an m, but they're otherwise the same. So what we need to do now is figure out what my derivatives with respect to x, n with respect to x, and m with respect to y are. And again, we've already done that work here. Subtract them and see what that looks like. And once I know what that looks like, because I have the same numerator in both of these, right? Once I know what that looks like, I'll I'll take a minute and compare m and n and see which one I'd rather divide by, and that will help me make my decision about whether I'm going to assume u is a function of x or u is a function of y. So I'm going to, let's see, I think I'll erase the whole bottom of the screen now because we've done the theory, and I want to work through the rest of this problem using what we now know about the assumption that u is either a function of x or y, but not both. In fact, I'll make this note here. If u is a function of x and y, we can't do these. Right? So we have to make this restricting assumption in order to carry on in this course. They can be solved, it can be done, but not here. All right, so I'm going to erase the bottom half of the screen, and then we'll finish the rest of this question here. All right, I've put a nice little yellow highlighted box around the important information here. Notice again that both of these have an n sub x minus m sub y and an n sub x minus n sub y. So let's take a look at what that looks like here. N sub x, we've already discovered, is 2x, and m sub y is 3x squared plus 2x plus 3y squared. I should probably note that this is n sub x minus m sub y. And then if we simplify that, we get 2x minus 3x squared minus 2x minus 3y squared. And these two cancel, which leaves me with, I don't want that, leaves me with negative 3x squared minus 3y squared. And that is negative 3 times x squared plus y squared. And that, so I can write my fraction, either this one here or this one here, as negative 3 times x squared plus y squared over either negative n or m. Well, negative n would be negative x squared plus y squared, and m would be this whole expression here. And if you look at this, if you look at what we have here, it's very similar to n. So I'm going to choose n. I'm going to choose, actually I want negative n, right? So I want negative x squared plus y squared, and then these cancel. So in this case, I have selected to assume that u is a function only of x, not a function only of y, which is the other option. And the reason for doing it that way is simply because it's convenient, right? This n is very much like the numerator once it's simplified. So this gives me 3. So what I've got here, if you look at this, back at this sort of formula here, is u sub x equals this expression here, n sub x minus m sub y over negative n. That turned out just to be 3 times u. So I have u sub x equals 3 times u. U sub x equals 3 times u. Why does it matter so much? Why do we care? Well, ultimately, what we want to find here is u, right? And so right now what I've got is an expression for du dx. Let's actually, let me change that. It's actually technically the partial of u with respect to x, but because there is only one variable involved here, right? We're only dealing with x's in these expressions. I guess I could get away with saying du dx, and that's equal to 3u. Well, we know how to solve those, right? Multiply both sides by dx, divide both sides by, okay, I'm changing it to d, apparently. Divide both sides by 3u, so I get du over 3u. Divide both sides. And so my new equation is 1 over 3u du equals dx. And that I know how to solve, right? That's just going to give me the natural log, well, let's see, I'll do it this way. 1/3 the natural log of u equals x plus c. Let's multiply both sides by 3. ln of u equals 3 times x plus c. So exponentiating both sides gives me u equals e to the 3x, and I'll just go ahead and distribute, plus 3c. That means that u equals k e to the 3x. I have now a function of u, which, as I assumed up here, is only a function of x, right? This is only a function of x. K is just a constant. So having made this assumption and used the theory that we talked about in the previous slide to determine what this ratio was, setting that up, I can now solve for u. I can find out what the function u is that I need. The problem is that now that I've got u, I have to start all over again. I have to take u and use it here, multiply it through all three of these expressions. And I haven't solved the differential equation yet. I've only found the integrating factor. So that's what I'll do next. I also want to make the observation that any one of these solutions will work, right? We have an infinite number of them. K can be any value, any real value. And so I'm just going to choose the one that's most convenient for me, and that is when k is 1. So I'm going to be using u equals e to the 3x as my integrating factor. That's what's going to go in here. So I'll do that next. All right, I've erased all of that, but I've copied my function u that I'm going to use up here. So we have that to refer to. And then I'm going to do this distribution. Well, I'll start by just writing u out. So I'm rewriting this line here, but I'm writing it with the knowledge of what u is now. So I've got e to the 3x times 3x squared y plus 2xy plus y cubed plus e to the 3x times x squared plus y squared times y prime equals 0. And now I should probably confirm before I go on that the derivative of the left-hand side with respect to y, not the left-hand side, sorry, this first expression, my new m, the derivative of that with respect to y is equal to the derivative of the other expression with respect to x. So let's do that real quick. The derivative of this with respect to y, when I take the derivative of an expression with respect to y, partial derivative with respect to y, I'm going to hold x constant. So this entire term factor here is a constant. This x is a constant, and this x is a constant. So that means that this 2x is just a coefficient of y. This 3x squared is a coefficient of y. So the derivative of the left expression with respect to y is the first, this is a product, right, times the derivative of the second with respect to y. 3x squared is a constant. 3x squared is a constant, so it's a coefficient. Plus 2x is a constant, so it's a coefficient. Plus 3y squared. That is the derivative, partial derivative of m, we'll say. Actually, let me just write it this way. This is my m sub y, my new m sub y. Having created or found and then applied the integrating factor, the expression I'm calling m changes. This was m sub 0, remember? And this is m sub 1. So this is my m sub 1 sub y. I'm just going to call it m. And this one here, once I find it, will be my n sub x. All right, let me go back and address this one again, because I have the first times the derivative of the second. This whole expression here is the second factor in a product. So I've just applied the product rule. The first times the derivative of the second plus the second times the derivative of the first, but that's going to be 0 because I'm partially differentiating with respect to y. All of this is a constant. Okay, so now I'm going to differentiate this side, or this expression, with respect to x. And now y is a constant, x is not. So when I take the derivative, I have the first, which is e to the 3x, times the derivative of the second with respect to x, that gives me 2x here, plus the second x squared plus y squared times the derivative of the first. And the first is 3e to the 3x. The derivative of that, partial derivative of that, with respect to x is 3e to the 3x. And simplifying that gives me, let's see, let's factor out this e to the 3x, and that leaves me with 2x plus 3x squared plus 3y squared, and that is, in fact, this new expression here is the same as this new expression here. It's a little out of order, but it's the same. So I've confirmed that by finding the correct integrating factor, I have produced what is now an exact differential equation. So now I can go back in and solve that differential equation. Most of the time, you will probably assume that having found the integrating factor, this is exact, and you can just carry on. But I'll say it's not a bad idea to confirm it, because if you got something wrong in the process and you integrate and you introduce a factor that's not the right factor, and this turns out not to be exact, you won't be able to carry on. You won't be able to solve it. So I'm going to erase a little bit here. I've confirmed what I needed to confirm. This is now an exact differential equation. And what that tells me is that there's a function out there whose first derivative with respect to x is this thing here. Now, a minute ago, we took the derivative of this thing with respect to y to check it against the derivative of this thing with respect to x. But now what we want to say is kind of the opposite. I want to integrate this with respect to x to find a function whose derivative is this thing with respect to x. And there's a function out there whose derivative with respect to y is this thing right here. But those two functions are the same, right? So let's see if we can figure out what those are. There is a function out there whose derivative with respect to x is this thing, which means if I integrate this thing with respect to x, I should get that function. And there's a function out there, and it's the same function, whose derivative with respect to y is this thing right here. So if I integrate this function with respect to y, I will get that function. And importantly, the answers to these two problems must be the same. Okay, so once I do this integration, these two functions, the results of these two integrations must be the same. So let's set these up real quick. I have e to the 3x, 3x squared y plus 2xy plus y cubed, and e to the 3x x squared plus y squared. And both of these are products. So my initial instinct is to use integration by parts. I'm not actually going to do these here. It's a bit tedious and a fairly complex process to walk through. The point of this video anyway was to show you that if a differential equation is not exact, there are times when we can make it exact. And the way to do that actually is really quite quickly. Once you have the right form, right, you know the form that it's in, and you check that these partial derivatives are equal. If they're not equal, you can very quickly subtract this work you've already done, subtract them, and divide by either n or m to find an integrating factor, which once you push it through, gives you an exact differential equation. So I'm not going to continue with this problem just because, well, for a lot of reasons, but the primary one is time. Let's take a look at one more example. Okay, this problem and the one on the previous screen were both just even numbered problems out of your textbook. The previous one I think was exercise 18, and this one is number 20. We're probably not going to solve this one either. The point here being to figure out, first of all, is it exact? If it's not exact, can you make it exact? And then if you can make it exact, what is the integrating factor that will make it exact so that you can solve it using that technique? So let's start by determining whether or not this is exact. What is the function that is attached to y prime, and that is this function here. And then what is the other function? What is the term that is not attached to y prime? And that is this one here, just a 1, just a constant. So I'm going to start by taking, I'll identify these first as m and n, and I'm going to take the derivative of m, the partial derivative of m with respect to y, and the partial derivative of n with respect to x. The partial of m with respect to y is 0. There are no y's in this, right? Even if there were x's would be considered constants in this partial differentiation, and so this would integrate to 0. Now, what is the derivative of n with respect to x? I think I'm going to rewrite this as x y to the negative 1 minus the sine of y. And then its partial derivative with respect to x, this term is going to be 0, right? Because there are no x's here. The y's that are here get treated as constants, and the derivative of a constant is 0. So that's just 0. In this term, I'm going to have, if I treat y as a constant, then y to the negative 1 is a constant, and the derivative of a constant times the variable is just the constant. So the derivative of n sub x, or the derivative of n with respect to x is just y to the negative 1 or 1 over y. Okay, now I don't need this anymore. All right, these are clearly not equal. So it's not exact, right? This is not an exact differential equation. But if I take n sub x and subtract m sub y, I'll get 1 over y minus 0, or just 1 over y. I want either n sub x minus m sub y over negative n, or n sub x minus m sub y over m. And as I think you can probably see, taking negative n would give me sine of y minus x over y. Putting that down here is going to make this very messy and quite difficult to, let me erase my, no, I don't want to erase, but I'll put this down here. My n sub x minus m sub y is just 1 over y. Right? That's the same for both. If I take my n and make it negative and stick that down here, I'm going to get this very messy expression. But if I take my m, keep it positive, and stick it down here, well, that's really quite tidy. So I'm going to stick with that one. I'm going to use this formula that produces just 1 over y. And what's critical here is that in addition to this being nice and tidy, it is a function of only y, not x. This one is still a function with an x and a y in it. So I couldn't use this one even if I wanted to in this class, right? So I'm gonna use this one, and I'm gonna make, I'll put a reminder up here. We said that this was what happens, or this is what we get when we assume that our u function is, I can't write today, having trouble with my penmanship, a function of, in this case, y only. In the previous example, we did one where we found that dividing through by m, or negative m, was tidier, and that was a case of assuming that our u function was a function of x only. Here we have assumed that u is a function of y only. Also on the previous screen, I chose a function to divide by. I chose to divide by negative, I can't even remember what it was now. I think it was n, negative n. I chose to divide by negative n because then the resulting expression simplified very nicely into one that was only a function of x. If I had chosen to divide by m, I would not have been able to do that simplification, and I would have been stuck then with a function that still had x's and y's in it. In this case, I can't simplify this one at all, and this one is really pretty much almost as simple as it can get, and there are no x's in it. So that means that really have to use this one. I really have to divide by m rather than n. I have to use this form of my formula, and that means that my function u, my integrating factor, is a function of y, not a function of x or of x and y, right? This one leaves me with x's and y's. This one gets rid of all the x's, leaving me with only y's. So now I have to figure out what my integrating factor is, and this is another place where it's really easy to leave something out. What I'm actually looking for in what is u sub y, because I'm using the version where I've taken the derivative of something with respect to y, right? I'm looking for, what is this? I'm looking for n sub x minus m sub y, in this case over m, times u. All right, remember from our first slide here, our theory slide, the way u sub y came out in that formula was this way, and it's really easy to forget to write this u here. Now that I know what n sub x minus m sub y over m is, I can write this as u sub y equals 1 over y times u, or I'll do it this way. My pen's not working very well today. There we go. I can write this as du dy equals u over y, or if I want, as u times y to the negative 1 power. So now I know what du dy. Now I know what du dy is. I'm looking for u, remember. How do I want to do this? I think I'll write it as u times 1 over y, because I'm now going to try to solve this very simple differential equation, and I think it's easier to see that what I need to do here is separate the variables. I'm going to move the dy over here and the u over here. I get 1 over u du equals 1 over y dy. My integrals were very messy there. So that gives me the natural log of u equals the natural log of y, and that implies that u equals y. So my integrating factor is just, the function u is just y. That means that I can rewrite this as y times 1 plus y times x over y minus the sine of y times y prime equals 0, and that simplifies to y plus x minus y the sine of y, got to keep my parentheses here, y prime equals 0, and that is an exact differential equation. We should probably double check that. I have a new function m and a new function n, and the derivative of m, I'll call this one m sub 1, with respect to y is just 1. And the derivative of n, this is m sub 1 and n sub 1. The derivative of n sub 1 with respect to x is the derivative of x, which is 1, minus the derivative of a product, but both factors of this product only contain y's. So with respect to x, the derivative is going to be 0. And I'm left with these two partial derivatives, and they are equal to each other. So this is now an exact differential equation. I'll go ahead and finish this one out. I'll show you the solution, but I'm not going to write out every little step on the screen. I'll start by noting, I'm going to erase some things here so that I have some more room. I've made my observation, right, that the two pieces that need to be equal are in fact equal. And then what I'm going to do is I'm going to observe that this function here is the derivative of some function with respect to x. So I have the derivative, I'm going to call that function f for now. The derivative of f with respect to x is y. And this other function, this other piece right here, is the derivative of some function with respect to y. I'll call that one g. The derivative of g with respect to y is x minus y times the sine of y. And then my job here is to go figure out what f and g are, and they have to be equal. All right, so f, since I've differentiated it with respect to x, y is a constant, which means that the original function, this was a constant on the variable, and so the function f must be x times y, plus a constant, but not really a constant, remember, because this function was the derivative of a function taken, sorry, this function here was the derivative of some other function taken with respect to x, which means that in addition to just a constant here, I might have an entire function, I'm going to call it h, only in terms of y. And when I differentiate that function in terms of y, partially differentiate it in terms of y, sorry, in terms of x, right, which is what I was doing here, I'm undoing that. If I differentiate h of y, a function only with y's in it, in terms of x, I'm going to get 0, right? So instead of a plus c here, I have a plus a function, but a function with the other variable in it. Now my g function must have been the antiderivative of this function. So the derivative of a function in terms of y, the derivative of a function in terms of y is x, because I'm dealing in terms of y, x was a constant. So that means the antiderivative is the constant times that coefficient, right? The variable times that coefficient. And then the antiderivative of y sine of y, I'm going to ask you to take my word for it for right now. This is a product, and so I had to do integration by parts to get this. But I get that the antiderivative of y sine of y is y cosine y. It's actually negative y cosine y minus sine of y. And then I have another situation where I have potentially a function entirely in terms of x, which when I differentiate it with respect to y will produce a 0. So these two functions are the functions I had to differentiate to get this y and this x minus y sine y. So how do I tell what h and k are? Well, we can make the observation. First of all, these have to be the same function, right? They have to be the same function. And so I can make the observation that these two terms are the same. Let me rewrite it this way. We have to say that xy, we have to know that xy plus this function h of y has to be equal to xy plus y cosine of y plus the sine of y plus some function of x, right? And if those two things are equal, then clearly we can cancel those terms, and we're left with h of y equals y cosine y plus sine y plus k of x. But h is only a function of y, so it can't have this term in it. It can't have a function in it that contains any x's. Okay, so we get this. And that means that this function here, my pen's not working again, there we go. This function here is really xy plus this function here. Well, guess what? G is also xy plus this function here. The other observation you can make is that the function f contains a function h of y, a function that only has y's in it, and you can see here that that's what that is. The function g contains a function that only has x's in it, and you can see from here that there is no such function. So we can ultimately rewrite, I've run out of room again, but we can rewrite our function as just xy plus y the cosine of y plus the sine of y, plus potentially a constant. Now remember from a previous video I said that we set that equal to 0. We could actually say subtract c from both sides. C can be any, potentially be any constant, so I'm just going to write that as equals c. And this is my final solution in this case. What the answer to this differential equation is. This differential equation, not having been exact, is something I might call almost exact, because I can make it exact by first testing the partial derivatives of m and n to see if they were equal. They are not. I can then determine what their difference is and choose a formula, figure out which one I'm going to use, figure out which variable that's in relation to. Don't forget to multiply by the u. Replace the factor that you found by doing this in this equation for your partial derivative. Integrate to get your integrating factor. Rewrite the problem with the, let's see, where did I go? Oh, we had to, I erased that, it was here. Then we had to integrate this to get the integrating factor. This is not the integrating factor. We integrated this problem. We solved this differential equation to get the integrating factor. It turned out to be just y. And then I multiplied both terms, all three terms, by that integrating factor, and now it's exact. I've also erased this piece. We confirmed that it was exact first, and then we solved it. So that is what I would call an almost exact differential equation, or a differential equation that can be made exact by the use of an integrating factor. It's a fairly involved process, and it's important to note that it's not something we can do very often. These are not terribly common differential equations, those that can be made exact if they don't start out as exact. But there is a strategy for dealing with at least some differential equations that might not be within our grasp otherwise.